Oh, hey, Meinolf. How are you today?
I'm very good. Thanks for having me, Charlie.
No, thanks for coming on. Now, what is it that you do and why do you do it?
Oh, that's a that's a broad question. Um, by upbringing, I'm an algorithmic computer scientist. So what really interests me, what fascinated me when I was young, is that if you program a machine, is that it does exactly what you want it to do. That was decidedly not my experience that I had with my fellow friends and family and brothers and whatnot. So it was kind of fascinating to see that there was a machine that to the dot would actually do what the program said. And then fascinated me. And it ultimately got me into computer science. And there, the most interesting piece for me was data structures, complexity, this whole question of how quickly can you actually compute something. Just because there's a solution doesn't mean that you can compute it, right? Or that you can compute it efficiently. And that then got me into what we would today call prescriptive analytics. So this whole idea of turning a problem description into what is the solution? What should you do? Right? What's the operational plan?
Hmm.
And from there, then AI sucked me in. So over via constraint programming, which is another declarative and prescriptive technology, to machine learning, because a lot of these problems that we're doing are actually search problems. And the question was, well, can't you have a hunch by using statistics and machine learning, all the way back to knowledge representation? And those are really the three pillars that get you from from data to value. You need to take the data, you need to represent it somehow, then you need to do some forecasting, and ultimately you need to make decisions. And that's where the money is. So right now where I'm working is on that last pillar, on making decisions. And at the core of it all is to believe that the machines that we have, computers, one of the biggest technical marvel that humanity has come up with, can do more than chat with you or play games or allow you to connect with other people. I want these machines to help us be more efficient, to tackle climate change, to tackle the demographic change that we're facing, and help humanity make better decisions in the face of uncertainty.
I mean, I think that's a really good altruistic, uh, output on this, viewpoint on this. But so we're obviously talking about the whole process of analytics there, and very much focusing on that last element of making decisions, making action for the output of solution. Can you give a sort of what would kind of a real life example of what that would look like?
Of course. So on the field that I'm talking about broadly is called operational research, and it's a very heavy name for something that's actually deeply beautiful. So think about you're running a company. Say you're FedEx, and you know exactly, hey, these are the parcels I need to deliver today. Now I have this many trucks standing around here. I have the following parcels. Which parcel are you going to put on what truck, and what route is that truck going to take? It's a really interesting problem because on one hand, you have the mathematical view to this. There is there's pure combinatorics at work here. So there is a finite set of solutions. There are only that many ways on how you can actually pack these parcels on trucks and drive them around. So that function has a minimum. There is a minimum cost solution to this question. What you put where? In reality, and this is what the computer scientist then looks at, is, well, okay, so yes, that set is finite, but it very quickly has more solutions than atoms in the universe. So I cannot actually do this. I cannot look at the whole solution space and do this. So now the question becomes, what can I compute? Can I actually have, and then complexity theory sets in. This is known as one of the hard problems, the so-called NP hard problems, for which we do not believe that if you increase the size of FedEx, you will still be able to solve these problems. But the name of the game is kind of pushing the frontier beyond of what you're actually facing in reality. And that's a typical problem. The issues we're facing with these traditional views of these problems is that they assume that everything was set in stone, right? So when you're solving this problem,
Mm.
like for FedEx, for example, you would assume that you know how long it takes to go from one client to the next when you're building that tour. And in reality, you do not know what the traffic is going to be tomorrow. And that's exactly what we are tackling in our company.
My first instinct would be is big data. How can big data be integrated into the machine learning to kind of counteract the different variables that's going on from just a lorry, so a truck going from A to B? That was my first instincts on how you would do that. But what would be your opinion? Would your approach to combating what seems like the impossible? 10 years ago, 20 years ago was the impossible question on how do you do that?
Oh, I'm not sure whether so. I think what we've overlooked and kind of conveniently defined away was this point that this data isn't set in stone, right? If you say you do production planning and you also have to set prices of your products, there are ways to model how your demand reacts to your prices. Right. And that was always kind of assumed that somebody comes and says, okay, somebody in the company already decided what the price ought to be. But they did this not knowing what your production constraints are, what your production capabilities are. So what they would do is very simply, they would say, oh, if I increase the price by X%, but the demand doesn't decrease by X%, then it's worthwhile increasing the price. And vice versa, right? If you're lowering the price and your demand goes by X% and the demand goes up by more than X%, you will lower the price. So somebody kind of comes in there. So this is like this product of price times demand, where you would say, oh, this is what I want to maximize. And this is what somebody else in the company would have done. And now you take those prices when you do the production planning. Now, if you have a really good company, there would be a revenue management department at the very end that would then say, yeah, guys, we're coming nowhere near the demand that we thought we could get for this price, so we might as well increase the price. But this is overall is not a good way of actually solving this combined problem of setting prices and scheduling your production. So I'm not sure that we even 10 years ago actually thought about integrating these. But now more and more through the everyday practice of data science and decision making in companies, we're getting closer and closer to doing so, because there are now data science teams that are coming up with ever more sophisticated models, for example, to forecast prices, to forecast traffic for tomorrow, to forecast all kinds of other things like demand for products in certain areas, etc. If you're running a warehouse system, for example, for inventory relocation, that's very important. And on the other side, you then have the folks who take these forecasts and try to make operational plans with them, right? When to relocate what, how to route your trucks, etc.
My favorite sort of case studies, and this is when I was studying economics, was we have a supermarket in the UK called Tesco. Now Tesco they've always had the monopoly in the UK when it comes to supermarkets, but they were also very a data-driven company, and there were always a really great case study around consumer behavior. Now this is just they did a whole different bunch of different innovations, but this is one of my personal favorites. On the 19th of May, the predictability that the UK weather will turn to over 20 degrees, it was always a consistent metric over the 10-year period between 2010 and 2020, or just sort of a little bit around that data range. And 20 degrees is when the UK population are most likely to go and have a barbecue, because it's the first sunny day. What we perceive as a sunny day, by the way, in the UK, I should always say that, because it's the first one. And so our first instinct is to go and have a barbecue, because it's not something we can do. And so that is exactly when Tesco will put the burger buns, the beer, the beef patties, the sausages, like crisps, all of these amenities, they'll put it at the front of their store, and they will stockpile in the 2 months with like the month two beforehand in order for this
Right.
date, because that's when it happens. And they
Right.
know this consistently happens, and then they obviously they bring in other economic models to say which products they're going to be pushing further ahead. So that's their order of events, and they did this for years, and it's made them a lot of money. And it's one of my favorite little case studies.
Yes, yes, yes. I mean, weather-driven patterns actually do matter a lot in industry, right? I mean, if I mean, it's the same in the United States. I mean, if you have a reasonable weather forecast for 4th of July, you know whether you need to put more soup or more orange juice out. And that's,
Yeah.
yeah. So better forecasts
Actually, it's
definitely
funny.
help. Yeah.
Yeah, I was going to say on the data, it's funny. I've had a client that was closely related to 4th of July. Now, what they did was drones. They did drone spectacles and drone shows. And you think, well, how is that related to fireworks? Well, because obviously they're event driven, like Thanksgiving and New Year and everything. But predictably, I knew every single year that the spike for fireworks goes like this. I'm doing this because this is what it looks like on my data. So every June, and May, I knew I had to put in a whole bunch of fireworks related content so that I would hit that 4th of July peak. That would just
Right.
hit for
Yes.
24 hours. You'd think this is the sales firework and this is the search around fireworks.
Right.
Yes,
Right.
I know that metric very well.
It is, what's interesting about it is that there is, when you're doing these forecasts, right, that ultimately feed into these decisioning models, is that there are really two kind of sources of information that you can use there. One of them is just you actually thoroughly understand how the world works. There is a holiday on the 4th of July where people actually, launch rockets and whatnot. That's kind of semantic, and it can be very annoying, especially for like jumping holidays. Really, really important, right? So if you're like a meat producer, for example, before Easter, for example, right? Everybody has their friends and their family over and whatnot, and so you're going to go shopping, and you probably overshop because you have a less predictable demand at home, so you overshoot with the whole thing. So you know exactly that the 2 weeks after Easter, you need far less meat than you need right before, because now everybody has their fridges full and leftovers left and right. And consequently, so right after you need to do this. Other events like this that kind of jump around is certain marketing and sales, right? So somebody makes hey, here's a reduction, right? So we kind of reduce the price for this product. You can also use it not just as something you need to react to, but also as something that you can actually control, that you can decide. So if you have too much inventory, you can actually make a special marketing thing, right? Put out a coupon, or if you really have too much of it, just give it as a gift to people who ordered something else. You just add it in there and say, hey, this is for you. These are kind of tactics you can play. But the interesting thing is those things you can kind of plan for. And then there are the other things like the weather, the traffic time is and whatnot, that you really have no control over. And that you need to integrate both of this information in order to, for example, do a reasonable demand forecast. So this is really interesting on this side of forecasting what's going to be and what you're going to want to optimize over. But what I'd like to stress is that there will always be residual uncertainty in those forecasts. Always. There's just, you don't have all the information. The future is not written, and there will be deviations from this. And that's kind of the vision for our company, is to say, well, let's get out of this. I know exactly what the future is going to be. Yes, you have an amazing data science team and they make great forecasts and it's wonderful, but they're never 100% exact. It's an impossibility. And now the problem is that the very fact that you are optimizing, you're really finding a super duper optimal solution for the data you were given, means that you're grossly overfitting this one scenario, this one future that you were forecasting. And that usually means that you're at the very edge of all the constraints, right? So if it's optimal, it means that you are at the limit of what is possible. And if that limit was estimated, there's a very, very good chance that you're over. So that means the very fact that you're optimizing for one select future means that you end up with a very brittle solution. And that is exactly what we're trying to get over. So we say, look, we actively take into account that there's some data that you have in the model that is guessed, that is estimated, and that it comes with a certain amount of uncertainty. Maybe we even know what that uncertainty is, how kind of these estimates truly distribute. And if we do know that, then we can actually build solutions and operational plans that hold up against a whole cloud of futures rather than just one. And that are still very good. So that's kind of what we're doing, if you want to put it in a nutshell.
No, absolutely, because that was the really big thing that came to my mind is how do you combat that probability of error that you know that there's going to be there. I mean, just even speaking out loud, knowing that there's going to be kind of some kind of error, there's going to be some kind of wiggle room that you're not going to quite hit it on target. It also prepares you for the real life decisions that you've got to make.
Yes.
Now,
yes, exactly. So I mean, there is a metaphor, if I may. If you're into soccer, you know that there are penalty shots, and you can actually go to The Economist, and they have a beautiful picture of a goal for soccer, where they analyze, I think from 76 to 2016 or something like this, like 50 years of soccer, 40 years in that case. 40 years of soccer penalty shots in the European championships and the global ones. And you can kind of see where was the shot aimed, and was it in, was it a miss, or did the goalie get it? Now, but that gives you a distribution on where penalty shooters shoot the ball. Now, guess where the expected ball is going?
I would say top right corner.
Well, no, the expected, right? Which would mean you take all the shots and take the middle.
Yeah.
It's the middle of the goal. So if you go by expected forecasts, if you don't take the distribution into account, you would tell the goalie, just stay put. The ball is expected to come straight at you. And that is, of course, nonsense. But that is what we currently do all too often. We go with expected values as opposed to understanding, oh no, this could be 100 or it could be 50, but it's actually never 75. Right? And that is really important to know when you're doing the optimization. So that's kind of, maybe makes it a little bit more tangible.
And so say, because we've been talking about a lot of data here, whether the data has been presented or you've got to go find this data within the weeds. But we were talking about the optimization. How do you even go about approaching knowing that you shouldn't go with the expected here, and that you actually should be going with the distribution?
So there are cases where the expected works, but it's increasingly rare. And even if you have an expected, you want to know how it distributes around it, right? So if typically, if your forecast was, this is the demand, for example, right? The demand forecast might actually be, look, it's at this price, it's probably going to be this, and then there's a small Gaussian distribution around. Yes, there are deviations, but they quickly wane off. You don't see too crazy deviations from that expectation normally. And you could have the opposite, right? You could have, well, this is my expected demand, but it's actually much more or actually much less. And that depends a little bit on the product that you're selling. Right? So there are, for example, if it's a seasonal item, you could have crazy demand for sun blocker or none at all. But wait, I mean, it's one of the two. I mean, it's when do you get the average expected? You practically never do. And that is sometimes true for certain products. This is not your razor blades. Right? For razor blades, the expected value is especially if you have a larger region, you can pretty much nail it down what the demand for razor blades is going to be. For sunblocker, it's a very, very different question. And so it kind of, there's domain knowledge that plays into it, but you can see it in the original sales data. And actually, the data science team usually knows that the expectations that they're giving you have no chance of ever materializing, or that they're actually very close. They can tell you that, and that's the beauty of it.
So what we're concluding here is actually knowing and understanding the industry, the market, actually understanding generally what we can. Is that right in saying it's like generally what we can predict, what we think, what we can assume is going to happen just from understanding and knowing what's been previous is actually not going to be too far off when we calculate the results.
Yes, so that is correct. I mean, typically, all these demand forecasts and everything else is kind of an extrapolation from the past. That's most typically what you see. You will rarely have forecasting models that predict you into a future that you haven't seen like it before. The key to making that work is to understanding what actually drives the whole process. So this is what we would call causal machine learning. It's a very, very interesting field, especially if you're working, for example, on actual physical assets, like my team did at General Electric. If you're looking at turbines for planes in the aviation industry, and you want to forecast when a turbine is going to need maintenance, of course, you have all kinds of additional understanding of how that system actually works. And you don't just need to go by correlations and going by what you've seen in the past, but you will actually use that additional knowledge in order to get you there. But I guess it is fair to say that most of the time we're actually going by correlations and just extrapolating the data from the past into the future.
Because even if we just slightly we focus on the turbines, there's so many different variables about the maintenance because you've got the probability of some of the faulty, if they say parts of the faulty machinery having been quite made, but they obviously the manufacturer will say a predictability on guarantee on how long certain materials will last through stress testing. But then if there has been a change in the weather system, so therefore there's like an increase of humidity or salt that's just been coming to the area that could again change the deterioration of the turbines. We could dig into just all these little details where if you're trying to send out a maintenance team and things aren't coming up as expected, these are some of the things that could throw a spanner into the works.
Yes, they greatly matter. I mean, also where you're flying. Right, so what's kind of the pollution in the air? If there are lots of little particles, you want to know that your plane has been flying there. How the plane has been flown. If you have a bunch of pilots that used to be fighter pilots, they tend to accelerate a little bit more than other folks, and that can really put strain on the thing. So it's all of the above. It's not just this and that many hours in the air, time for maintenance. It is way more than that. Yes.
Now, so for most people, I'm talking for people who are not necessarily, who don't live in the data world, and they have a problem to solve. Now, let's say they don't necessarily have an extensive data team or knowledge like yourself to basically go and find those answers. What would you suggest to them? Would it be to take all of the data or know which data to be looking at?
So, compared with buying a car, okay, before you buy a car, you should actually ask yourself a couple of questions. Number one is, do I have to be at certain places regularly that the car can take me to? So for the data world, that means, do you have a problem that you need to solve over and over again for which you're going to need a forecast? if you don't have that and it's like a one-off, it's kind of a stupid idea to try and solve this on your own. You should go and get outside help. Just buy it, right? The second question is there gasoline where I want to go with my car? So the equivalent for data science is there data? Is there data that will actually allow me to predict that thing that I need to predict? And that data better hold signal. That shouldn't be something you have on your shelf anyway, where you kind of go like, oh, well, maybe I can do something with it. That's not good enough. It needs to support the question that you actually need answering. And then lastly, are there roads or not? Because if you have a car and you're in a place where there are no roads, then what the heck are you going to do with a car? You might still have to go someplace and you might even be able to buy gasoline, but if there are no roads, it doesn't help. The equivalent in a business is, will somebody pick up these forecasts that I'm making? Or the decision plans, right? So it's the same thing. Operational research definitely falls under this also. It's not just forecasting. Because if nobody picks up the operational plans that I came up with, then why did I make them in the first place? So if you need to overhaul your entire business so that it can consume the insights that you're generating with AI, then you might as well not bother, unless if it is absolutely existential for you to do so. I mean, if you will be out of the business, unless if you overhaul your entire operations, fine. But otherwise, you don't want to do that, because otherwise you have a very expensive data science team sitting around there, with people massaging the data, representing the data, making forecasts, making decisions, and they come up with really beautiful things. The problem is nobody picks that up and implements. So those are kind of the three questions that I would ask anybody who thinks about standing up a data science team to ask themselves first.
I think that's a great summary, and absolutely, people will be writing that down and really making the most of the data. And I want to sort of flip it back onto yourself and your business. For the final questions, now, can you just tell us a little bit more about your business, and what's the vision in the future for what you're looking to achieve?
So we've had the same kind of technology which was invented in the 1940s, 80 years ago. Practically run all of our decision analytics. And it's called mathematical programming, mixed integer programming. This is really the workhorse of making operational plans, of decisioning in industry. And the main problem that they have, there are many. One of them is that, yes, they come with a provable optimal solution, but that is to the model that you feed them. And the model is very restrictive. It basically has to be a linearization of everything. You can linearize a lot if you have integer variables, but it quickly becomes very large. It becomes cumbersome to solve. So you're cutting corners. You're kind of doing an approximation of the real world in order to shove it into these systems. And of course, they take that data that you give them for granted. This is what I'm supposed to optimize. And then you will come back with this very brittle, right at the corner of everything that's possible solution, because that's the provable optimal solution that you have. And that's not good enough in this day and age. In reality, we are not doing this in isolation when we're decisioning. We're doing it on the shoulders of machine learners and knowledge representatives. And so the realities, put them realities or forecasts if you want, that we're being fed are estimates. And the problem now is that you need more robust solutions. So that's kind of number one. You want to also make it easier to model these problems. So rather than having to linearize everything, you want very, very strong modeling concepts that make it easy to just write down what your problem is. So maybe I should say this really quick. The idea behind this is, of course, that you don't sit there and you actually write the algorithm that finds the solution. The paradigm when you come to this decisioning piece is what's called declarative programming. So what you do, instead of saying, hey, computer, this is how you find me a good tour for FedEx, for example, what you say instead is, hey, this is how long it actually takes to go from one place to the next. or what my distribution is for going from one place to the next. Find me a good tour, and you define kind of what a tour is supposed to be. So rather than saying how the computer finds a solution, you tell him what properties the solution should have. This is called declarative programming. And that, of course, makes it possible for laymen to just define what the problem is. You just say what you want and what your objective is and what your constraints are in terms of what is legal to do, what could you execute. And if you put those three pieces in there, the computer then goes and finds a really nice solution. So with that being said, apart from the whole uncertainty piece that I was mentioning, really the vision 10 years, 15 years from now is that this kind of technology permeates the industry far more than it has. Because so far, this kind of technology is really limited to large companies that can afford a data science team that have experts or are experts doing this. But why isn't every mom and pop shop doing their pricing and production planning using this technology? It's been prohibitively expensive to do. It's been prohibitively difficult to use. And that is where I ultimately want to be. So if Inside Op really takes off, I hope that in the future, using a solver costs $100 a year. So everybody can afford it. And that it's just excruciatingly easy to model, potentially even with LLMs.
I mean, that's exciting. That is
Yeah.
really, really exciting.
Yes.
And like you said, just sometimes a lot of these, barriers and challenges for the smaller business is just the accessibility to the more advanced technology, and
Yes.
that's what we're really talking about here. And as that becomes far more mainstream, it becomes far more exciting because it's 95% of majority of the economies, which are these between 1 and 10 size companies, employee size companies.
Yes.
And that's the more this is kind of one of the missions of the podcast. The more we can help the 1 to 10 size companies, the better the economies will be, the better your
Yes.
friend, your neighbor, your
Yes.
the society and community will be just better overall. So that's exciting to me. That's really exciting. Well, Meinolf, it's been an absolute pleasure for you to be on the podcast. I think we've really, really dug into some really good subjects and information that people will get a ton of value for. So thank you for coming on. Now, final last question. Might be a little bit tricky to answer, but we'll ask it anyway. What is something that somebody can buy from you today that is under $100 that would add a ton of value to their life?
A T-shirt.
Is it a bit of a one? Yeah.
It is. Look, no, we don't have anything on the shelf that costs under $100. I fear. This is the vision where I want to be. But the truth of the matter is, if you're starting out, you have to prove your value, right? So, this is a little bit counterintuitive to founders, because they usually think you shouldn't be doing anything that doesn't scale, right? And the opposite is true. When you're starting out, you need to work with some few clients, not the mass with a huge tail for which you could offer something for $100. You start out with few clients and understand them extremely well so that you understand what your product needs to look like so that it will also work for the tail. But you need to do that work. But that work is painstaking and very, very expensive. So if you want to get yourself over that hump, you need to be in a different operational mode than the one that you're aspiring to in the long run. So right now I fear no, I really couldn't, put out a solver for $100 at this time. But
No, but I think
the
I think
more
that is
people buy it,
perfect advice. I think that's perfect advice because it's usually the anti-intuitive. People want to kind of start up and scale and grow quickly, when actually having that small group of paying clients of the niche you want to really operate in and get to know them incredibly well. And also, I'm going to just jump on it a little bit more and say, make their lives so easy and seamless and frictionless. That the whole operation is so slick and inside out. When you get to thinking, okay, how do I want to scale and grow? Oh my, there's going to be so little stress cracks in
yes,
that foundation and base that when you scale and grow, it's going to be a far easier journey than if they were there.
So
So I think that's beautiful.
don't get me wrong. I'd be thrilled if we scale very, very quickly. The point that I'm trying to make is that in these early days, you operate differently than what you will 2 years, 3 years from now when you have scale. And that's needed, right? So just because you want to scale doesn't mean that you operate in the same way when you're little as you will operate when you're really large.
Oh, brilliant. Thanks so much for coming on the show. And I'm sure we can dig into another episode another day. But in the meantime, have a fabulous Friday.
Thanks for having me, Charlie, and good luck with the podcast.